Welcome to The Explainer. Today we're looking at something that, quite literally, supports our entire modern world. I'm talking about soil mechanics. Okay, let's dive into this. We walk on the ground, we drive on it, we build these massive structures on top of it, and we totally take for granted the intense engineering required to make sure the earth beneath our feet actually stays put. So today we're going to explore one of the absolute most fundamental experiments in geotechnical engineering, the direct shear test.
Think about that for just a second. When a civil engineer designs a sprawling skyscraper, or maybe a highway carved right into a mountainside, or a massive dam holding back millions of gallons of water, how exactly do they know the ground won't just give way? How do they prevent catastrophic landslides or sinking foundations? Well, they can't just guess, right? The stakes are incredibly high, and it really all comes down to a rigorous testing process that tells us exactly how much stress the soil can take before it ultimately fails.
To answer that question, we've got to understand a core concept called shear strength. Essentially, shear strength is the maximum resistance that a material can withstand when it's subjected to shearing forces. Imagine taking two blocks of really rough sandpaper and sliding them against each other. That friction, that resistance you feel, that is shear strength at work. In our environment, it's this invisible microscopic force happening between grains of sand, silt, and clay, and that is what keeps slopes stable and buildings standing tall. If the shear stress applied by a building exceeds the soil's shear strength, the soil shears apart and, well, the structure falls. So here's our roadmap for this explainer. 1. The science of shear strength. 2. Real-world engineering stakes. 3. Direct shear versus triaxial testing. 4. Running the experiment. And 5. Analyzing the lab results.
All right, part 1, the science of shear strength, the forces beneath our feet. So, the entire objective of our experiment really boils down to estimating two highly specific parameters. We're looking for the angle of internal friction and the cohesion of the soils. These two metrics are basically the DNA of soil stability. Cohesion is all about how well the soil particles naturally stick together. Think of clay, right? It's highly cohesive. The angle of friction, on the other hand, is about the physical interlocking of the particles. Think of gravel or sand. Together, these two numbers dictate exactly how a specific batch of dirt is going to behave under the immense stress of a construction project.
Moving on to part 2, real-world engineering stakes. Why this data matters.
Because look, we aren't just collecting numbers for the sake of science here. These are massive engineering challenges. We're talking about real, practical applications. First up, assessing the stability of slopes or cuts. If you're cutting through a hill to build a highway, you absolutely need the shear strength to know what angle to cut the dirt so it doesn't just collapse onto the cars below. Second, finding the bearing capacity of foundations. This tells us exactly how heavy a building can be before it literally punches right through the crust of the earth. And third, determining earth pressure on a retaining wall. If you're building a wall to hold back a hillside, the shear strength of that soil dictates how thick and reinforced that concrete wall needs to be so it doesn't just snap under the weight of the earth.
Section 3, direct shear versus triaxial, choosing the right test. Now, what's really interesting about this comparison is that engineers constantly have to weigh precision against practicality. The direct shear test is incredibly popular because it's simple, it's quick, and it's inexpensive. You can use it on undisturbed or remolded samples when you just need a fast, rough estimate. But it does have a fatal flaw. It forces the soil to fail along a predetermined joint in the testing box, which, might not actually be the weakest part of the soil. On the flip side, the triaxial test is much more complex and highly accurate because it doesn't force a predetermined failure plane. Because of this, the triaxial test is often the go-to for major, critical projects where highly accurate estimation is just paramount. However, the direct shear test still remains a brilliant foundational baseline for geotechnical engineers all over the world.
All right, part 4, running the experiment inside the lab with ASTM D3080.
So, setting up the shear box apparatus is a very tactile, very precise process. First, we carefully weigh the initial mass of the soil. Second, we measure the diameter and height of the shear box, and we mathematically compute exactly what 15% of that diameter is in millimeters. And hey, keep that 15% number in mind, because we are definitely going to need it later. Third, we assemble the shear box inside the direct shear device, dropping in a porous stone and some filter paper. Finally, we pour our sand into the box, level it off perfectly, and top it with another filter paper, another porous stone, and a top plate featuring a small metal ball.
Okay, so with the soil perfectly sandwiched in there, we prep for the dynamic testing phase. We remove the large alignment screws holding the box halves together,
Then, we use gap screws to open a tiny gap of approximately 0.025 inches between the top and bottom of the box, and then we back those gap screws right on out. We complete the assembly by initializing our 3 gauges to absolute zero. That's the horizontal displacement gauge, the vertical displacement gauge, and the shear load gauge. We apply a predetermined vertical pressure by closing the bleeder valve and raising a toggle switch. Then, the actual shearing begins. We start a motor that pushes the bottom half of the box at a constant selected speed, literally shearing the soil in half. And as this happens, we meticulously record the readings on our datasheet.
And this test continues until one of two things happens. The motor keeps grinding away until either the horizontal shear load peaks and then clearly falls, which indicates the complete structural failure of the soil, or until the horizontal displacement reaches exactly 15% of the sample's original diameter. Remember that number? Yeah. Once we hit that 15% mark, the physical experiment is officially complete.
Section 5. Analyzing the lab results from data to engineering report. Let's move to the analysis and see how this all builds together.
To get a truly accurate picture, engineers don't just run this test once. They run multiple samples of the exact same soil under varying vertical weight, which is known as normal stress. For instance, we might run a first test at 14.3 psi, a second at 28.9 psi, and a third at 43.5 psi. By varying this normal stress, we can track how the variation of shear stress changes with displacement. We take all these different data sheets and we plot them onto a single graph, creating a super clear visual of shear stress versus normal stress.
So the crucial point here is that all of that physical shearing, all the motors and dials, all the careful plotting of 14.3 and 43.5 psi, it all culminates in extracting our ultimate output. We use our final plotted graph to mathematically determine the cohesion and the angle of internal friction of our soil sample. These two parameters are then handed over in the summary and conclusion of our lab report. And with those two numbers in hand, civil engineers can confidently pour concrete and build our modern world safely.
It is just incredible to think about the invisible science operating right below the pavement. So I'm going to leave you with this final thought. Next time you walk into a towering, massive skyscraper, ask yourself, what is the angle of friction of the earth holding it up? Thank you so much for joining me for this explainer. I really hope you found this breakdown of the direct shear test as fascinating as I do. Keep questioning the world around you.
Shearing, all the motors and dials, all the careful plotting of 14.3 and 43.5 psi, it all culminates in extracting our ultimate output. We use our final plotted graph to mathematically determine the cohesion and the angle of internal friction of our soil sample. These two parameters are then handed over in the summary and conclusion of our lab report. And with those two numbers in hand, civil engineers can confidently pour concrete and build our modern world safely.
It is just incredible to think about the invisible science operating right below the pavement. So I'm going to leave you with this final thought. Next time you walk into a towering, massive skyscraper, ask yourself, what is the angle of friction of the earth holding it up? Thank you so much for joining me for this explainer. I really hope you found this breakdown of the direct shear test as fascinating as I do. Keep questioning the world around you.